Hello everyone, today in this video we are going to talk about electric field of a dipole. So after this video you should be able to define what is a dipole and a dipole moment, and you should be able to calculate the electric field due to a dipole. So before we go into the dipole, let's do a quick recap of electric field. So electric field is a region around a charge where it can exert force. So outside that region it cannot exert the force on other charges, and this is the expression for electric field: force per unit test charge. And electric field is a vector quantity, and the direction of electric field is same as that of electrostatic force. And this is the expression for electric field due to a point charge, and this is similar to Coulomb's law, only we don't have the second charge out here. And the unit of electric field will come from here, that is Newton per Coulomb. And the electric field depends on the amount of charge and the distance from the charge. So for small charge we have small electric field, but if you take a larger charge, the electric field due to that at the same distance will be more as compared to the smaller charge. And if we go far away from the charge, the electric field decreases like this. So out here the electric field is more, but the far away from the charge electric field is less, meaning if you keep a test charge out here, there will be large force on this test charge, and if you keep another test charge out here, the force on that test charge will be small, because electric field is force per unit charge. As the electric field decreases, the force also decreases. And the direction of electric field is away from a positive charge, because if you leave a test charge out here, it will be repelled. And in case of negative charge, the electric field will be directed towards the negative charge, because a positive test charge will be attracted towards the negative charge. And this is the superposition theorem. So if you have many charges, then electric field due to that many charges will be given by the superposition theorem, and the total electric field will be the sum of electric field due to individual charges. Now we will talk dipole is nothing but two equal and opposite charges separated by some distance. So this is a dipole. Di means two, pole means end. So this is a system with two equal and opposite charges separated by some distance. And the total charge or net charge of a dipole is 0, because if you add this plus q and minus q, you will get 0. And ideal dipole means two equal and opposite charges separated by very small distance. So out here you can see positive and negative charge, and the distance between them is very small as compared to this large dipole. And now these are the real life examples of dipoles. Some molecules like hydrochloric acid and water molecules are the examples of dipole. Out here you can see hydrogen is slightly positive because it donates one electron to chlorine, and the chlorine gets the electron and become negatively charged. So this system is a dipole. Similarly, the water also has the property of dipole. Now next is electric dipole moment. So if you want to find the electric dipole moment of a dipole, then you have to multiply one of the charge with the distance. So out here you can see, so distance is 2a and charge is q. Dipole moment is denoted by small p is equal to 2a into q. 2a is the distance, q is the magnitude of one of the charge. And electric dipole moment is a vector quantity. So by definition, the electric dipole moment is the vector with magnitude which is equal to the product of either charge and the distance between them. So this is the formula, either charge into distance between them, and p is equal to q into 2a, but we write this as p is equal to 2aq, and unit is, so this is the distance and this is the charge, that is Coulomb meter. And dipole moment is a vector quantity, and the direction is from negative charge to positive charge. So the direction of dipole moment is from negative charge to positive charge, and the direction of dipole moment is same as the direction of distance vector, and distance vector is from negative q to positive q. And the significance of dipole moment. Now if we know the dipole moment of a system, then it will be easy for us to know how it will behave in electric field, or this term is called polarization. So when we keep a dipole in electric field, it will rotate according to the electric field, and this term is called polarization. So in coming chapters we will discuss this in details. So for now we have to understand, by knowing the dipole moment we will know what a dipole will do in an electric field. So now we will find the electric field due to a dipole. So there are two positions where we are finding the electric field. One is this line, we call it axial line because it is passing through the axis of the dipole, and another is equatorial line. So this line is a perpendicular line passing through the center of the dipole. So we can say it's a perpendicular bisector of a dipole. So now let's find the electric field of a dipole in axial line. So I am considering a dipole with charge plus minus q, and the distance between them is 2a. So I am not denoting this distance by r because the distance r will be taken as the distance of point where we are finding the electric field. So 2a is the distance between two charges. So this is the center and this is the axial line, and this is the point P where we are finding the electric field, and the distance of this point P is r from the center of the dipole, and this distance is a because whole distance is 2a, so half of the distance is a, and this side is also a. So distance of P from this Q will be r minus a, because from here to here is r, but we are interested in this distance, so this is r minus a. And similarly from minus q, the distance of P is this r plus this a, so this is r plus a. And electric field at P due to this positive charge will be towards the right, and I'll denote it by E plus because this is due to positive charge. And similarly electric field at this point due to this will be directed towards the left, and I'll denote it by E minus. And as you can see, this charge is nearer to point P, so the magnitude of the resultant will be E plus minus E minus, because this electric field E plus is more because this charge is nearer, so the total resultant electric field will be the difference of these two electric fields. So now let's see. So this is the same diagram I have used. So I am considering a point P at distance r, and the charge of the dipole is plus minus q, and the length of the dipole is 2a. So electric field at P due to plus q is given by, so E plus is k q by distance square, and distance is bp square. So I'll put the values now. K, q, and the distance is r minus a whole square, and the charge is q. Now similarly electric field at P due to charge minus q is given by this, so I am not writing minus q because I am finding the magnitude only, not the direction. Now when we put the values, you will get this, and the direction will be towards P to A, and for this it was from B to P. Now the resultant at this point will be the difference of these two electric fields, so I am not writing vector because I am finding the magnitude, and EA means electric field at axial line. So now after putting the values, now I'll take k, q common, I'll take the LCM and solve this. So this will come up, this will go up, and these two will get multiplied. Now I'll open this bracket. Now I'll square these two terms. So now I'm writing this bracket because of this minus sign, so I'll multiply this minus inside, and out here you can see this is a plus b and this is a minus b. So I am using the formula of a plus b into a minus b, that is a square minus b square, and I can cancel this a square and a square and r square and r square. So I am left with ea is equal to k cube 4ar r square minus a square whole square. Now I'll multiply this inside. So now this 4a, I can write this as 2 into 2a, and we know 2aq is equal to p, that is electrical dipole moment. So I'll put p out here, so you'll get this. So this is the total electric field, and this is along bp, because the direction of the larger vector, that was E plus, was from B to P. So the resultant will be in direction of larger vector. Now if we consider this dipole to be very short, ideal dipole, so out here this distance is big, so I'll consider another dipole where this distance is very small as compared to r. So r is very large, r is large out here. In our previous case, distance r and a was comparable. Now the r is large, so I can neglect this a because it is very small as compared to r. So out here I can neglect a, so we'll get this ea is equal to k 2 rp by, so instead of this a I'm writing 0, so r square whole square, so it will come as r to the power 4. Now this r and 1 r from denominator can be cancelled, so I'm left with r cube. So this is the total or final electric field due to the dipole at the axial lines, and the direction is bp, so that is from negative charge to positive charge. Now in vector form I have to give the direction. So direction we already know, from b to p, that is from negative charge to positive charge. Direction from negative charge to positive charge is the direction of electric dipole moment, so I am giving the direction of electric dipole moment, that is from negative to positive. So next is electric field at the equatorial line. So this is the dipole plus minus q separated by a distance 2a, and this is the center. So from center I am drawing a line. This is the equatorial line. I am keeping a point P. So this distance is a, and this side is also a, and this distance will be root over a square plus r square, because this is r, this is a. So this is the hypotenuse is equal to root over perpendicular square plus base square. Similarly, this distance is also root over a square plus r square. Now the electric field at this point P due to this positive q will be away from the charge, that is this direction, and electric field at this point due to minus charge will be in downward direction. So now we have got the two vectors at a point, so the resultant of these two will be given by the resultant vector and EE, electric field at equatorial line. And if this angle is theta, this angle is also theta, and this angle will be 2 theta, because the external angle is equal to sum of opposite internal angles. So now we will use this diagram. I am considering a point P at equatorial line at distance r from the center. So these are the things which I have considered. Charge is plus minus q, length of the dipole is 2a, and the distance, that is AP or BP, is root over a square plus r square. Now the electric field at this point due to positive charge will be given by this. I have to put the value of BP square. This is BP or AP, so I am using this, so I can cancel this square and this root over, so I am left with this, and the direction will be from B to P, and I will denote this by E. So I am considering this to be E. Similarly, the electric field at this point due to the negative charge will be given by this expression. Now I'll put the value of AP, then we will get this. So again this is same as E plus, so I'll consider this to be E. So magnitude of electric field due to positive charge and the magnitude of electric field due to negative charge is same. So that is why I have written this to be E, so that it will be easy for me to do the further calculation. Now you can see at this point I have two vectors. So from here there are two ways to find the final electric field. So I will explain both the ways and you can take only that method which you find easy. So out of two you will find the easiest one, but I'll explain both. So now in first method we will use the triangle law to find the final vector. So out here you can see one of the vector is going in this direction and another is going in this direction. So the resultant of these two vectors will give me the final electric field. So this is the triangle law. Resultant square is equal to a square plus b square plus 2ab cos theta, and angle between these two vectors is 2 theta. Now as the magnitude of E plus and E minus were equal, both the electric fields were equal, only the direction was different. So I can use E for E plus and E minus. So I am putting E. So I will add this 2 square and I will multiply this. So now I will take 2e square common. So I am left with 1 plus cos 2 theta. Now I will multiply and divide this with 2 because I want to take this 2e square out of the square root. So multiplying and dividing. So this 2 and this 2 will become 4 and this 2 will remain in denominator. Now this 4 means 2 square, so I can write 2e whole square. So now I can take this out of the square root. So I am left with this. Now we have to take care of this part, and we have one formula. 1 plus cos a by 2 will be given by cos 2a. So out here our a is 2 theta. So instead of this term I can write cos 2a by 2. So now I am using this formula to remove this root over. So now this 2 and 2 will get cancelled. So we are left with 2e cos theta. Now I have to put the value of e and cos theta. So we already know the value of e, which we have found out. Now out here you can see the cos theta will be given by base by hypotenuse. So base is OB and hypotenuse is BP. So now if you put the value of OB and BP, then OB is A and BP is A square plus R square whole root over. So now for root over I can write power half. Root over means power half, and for this I am writing power 1. Now I can add the power of these two because they are having the same base, so I can add the power. So it will be 1 plus half. So now instead of 2aq I can write p, that is electric dipole moment. Now the final expression will look like this. So this is the final expression, and the direction will be towards the left from point P. And I am writing this by symmetry because these two vectors are equal and they were making angle 2 theta, so the resultant will make angle theta with one of the vectors. That is why I am writing by symmetry, because the angle will become half. And now if we consider this dipole to be very small like this, so out here you can see distance r and a was comparable, but if you take a very short dipole and if you take the distance r to be long, then we can neglect this a square. So if you neglect this a square, you will get this. So I am putting a to be 0 out here. So this 2 and this 2 will get cancelled, so I am left with kp by r cube. So this is the final expression. In vector form I have to give the direction. So we already know the direction was from positive charge to negative charge. So the distance will be the opposite of the distance of the dipole moment, because the dipole moment was from minus q to plus q, but our resultant is going from plus q towards minus q. So the direction is just opposite of the direction of electric dipole moment. So I'm just writing negative p cap out here. So the direction of resultant is towards the left from point P, that is from positive to negative, that is opposite of the direction of P, and that's why I'm writing minus p cap. As I have told you, there is alternative way also. So till here the electric field of positive and negative, the method will be same. So after this line we will do the alternative, that is second method. So you can take the method whichever you find easy. So this is the second method. So till here both the methods were same. Now out in this diagram I'll take only this part. So in this part at point P we have two electric field, one going upward, one going downward. This is making angle theta with the horizontal. Now this vector can be resolved into two vectors. One is vertical, that is E sin theta, and one is horizontal, that is E cos theta, and towards the angle will be the horizontal component, that is E plus cos theta. Similarly, this E minus can be resolved into two components. One will be E minus cos theta, that is horizontal component, and vertical component is E minus sin theta. As the magnitude of E plus and E minus is same, so these two components will also be equal, but they are going in opposite direction. So E plus sin theta and E minus sin theta are equal and opposite, they will cancel each other. So we are left with only E plus cos theta and E minus cos theta, and they are going in same direction. So if we add them, we will get the resultant. So if we add them, we will get electric field at point P due to the dipole. Now we can write at point P vectors E plus and E minus can be resolved into two components each. So this is the diagram I am using. So horizontal component will be E minus cos theta and E plus cos theta, and they are along the same direction. And vertical components will be E minus sin theta and E plus sin theta, and they are along opposite direction. So two vertical components cancel each other because they are equal and opposite, and two horizontal components are along same direction, they will get added to give the resultant electric field at point P. So we have to add E minus cos theta plus E plus cos theta. So this is the final electric field at equatorial point. Now I'll take cos theta common, and the magnitude of E plus and E minus are equal, so I can write E for them. So it will be 2E cos theta. Now the value of E is kq by a square plus r square, and cos theta is by hypotenuse, and our base is OB and hypotenuse is PB. And if we put the value of OB and BP and this k, we will get this. And now I'll put the value of OB to be A and BP to be root over a square plus r square, and this root over can be written as power half. Now we are having the same base in the denominator, so we can add the power. Instead of 2AQ, I can write P, that is electric dipole moment. Now when you add 1.5, you will get 3 by 2. So this is the final electric field at point P, and the direction is towards the left from point P, and it is making angle theta with one of the vector, because these two vectors are equal, and when we add them, the resultant will go towards the half of the angle, that is half of 2 theta, that is theta. So that's why I have written by symmetry. Without finding, we can directly write this. Out here the dipole was long and distance A and R was comparable, but if we take a very short dipole, that is R is large as compared to A, then we can ignore A. So we are left with this, and this r square and this 2 will get cancelled, so we are left with this. This is the final expression. Now in vector form, I have to write the direction of this vector. So the direction was from this point towards the left. Now we will compare the electric field at axial line and equatorial line. So for axial line the final expression is this, and for equatorial line at same distance r the expression will be like this. So if we divide equation 1 by 2, then we'll get this. Now I will reciprocate this and multiply this side. Now I can cancel r cube and r cube, p and p, so we are left with 2. So if you multiply this side, so electric field at axial line will be 2 times electric field at equatorial line. That means EA is greater than EE, because if you multiply EE with 2, then only it will become equal to EA. So EA is greater. So this is for the same distance R. So for the same distance, electric field at axial line will be 2 times the electric field at equatorial line. Meaning if you have 10 Newton per Coulomb at the distance of 2 meter from the center at the equatorial line, then at the same distance in the axial line, that is 2 meter, your electric field will be 2 times. That is, out here it's 10, so it will become double. So for the same distance, the electric field line at axial line will be greater than the electric field at equatorial line, and this will be 2 times. So now we will summarize the video. So this is the electric field at axial line of a dipole when R and A are comparable. That means our A is large. If the dipole is short, the expression will look like this. So we can ignore this A square. Similarly, electric field at equatorial line will be given by this when R and A are comparable, and when the dipole is short, we can write this. And electric field at axial line is 2 times the electric field line at equatorial line. And to find the total electric field at equatorial line, we have 2 methods. One is by using the triangle law, and one is by taking the vertical and horizontal component of E plus and E minus. So choice is yours. Whichever method you find easy, you can go with that method.